inelastic collision. And in that case, energy so in that case, energy is being converted. Might as well have this written in the board to keep track of what we're talking about. So yeah, elastic means kinetic energy is conserved. And inelastic collision, like if two cars crash together hard, right, then sure, you generate heat, but you also wind up changing the shape of the car, right? The car, I mean, sadly, right, and people get hurt and everything else, so don't do it. But when they get all mangled up, the cars, that is, the metal being bent and deformed actually costs energy, right? It takes energy to bend the metal and to bend it permanently. So if you push a spring and it springs back, you got your energy back, right? That's why we talk about potential energy for springs. If you push a spring too hard, if I stretch a spring too hard and deform it so it doesn't spring back to where it was, I lost that energy. That's not potential energy anymore. It got turned into heat, and it got turned into a changed configuration. I broke bonds or changed who's connected to whom, right? I broke bonds in the metal. That costs energy, right? So when we have collisions, when you're going through a physics problem, the first thing you want to do is recognize are there collisions or not in this problem. And sometimes it's surprising what constitutes a collision. So some students won't figure out that the problem is really this guy's collision problem. That's the first thing. Is it a collision or not? The next thing is, okay, is it elastic or inelastic? If it's an elastic collision, what I mean is that kinetic energy is conserved. So that means that you can count on the final kinetic energies all adding up to the initial kinetic energies, right? But sometimes you're going to have inelastic collisions. And there's different kinds of inelastic collisions. You can have inelastic collisions where some of the kinetic energy is lost. And you can have some elastic collisions where as much is lost as you can lose. So if you have a maximally inelastic collision, so we just first say inelastic. So if you have an inelastic collision, that means some kinetic energy was lost, right? If you have a maximally inelastic collision, all right, that means that as much as possible is lost, and in particular, all kinetic energy is lost if viewed from the center of mass coordinate system. So I'm introducing a lot of concepts right now. I'll say in center of mass, center of mass coordinate system. So what do I mean by all this? What is the center of mass coordinate system? All I mean is any problem you've got, you can find the center of mass in the problem, right? In fact, these problems over here are pretty easy for us to think about because the center of mass was actually holding still, right? This problem, the two balls were together, it's all holding still. After I lit this thing and the spring does its work on them, they spring up, they fly apart, but the center of mass continued to remain right in the center, right? Well, that means we were viewing this collision, this inverse collision, if you like, with from the center of mass coordinate system. Some people are squinting up at the screen. What's hard to read? Is anything not clear? Let me know if you guys can't read what I wrote. Yeah? No? All right, speak up if you can't read it. I'll tell you what it is. So in this case, we were viewing the system right off the bat, even though we didn't set it up that way, it just was conveniently that way in the problem description. We were viewing it from the center of mass coordinate system. Same thing here. We view this in the center of mass coordinate system. The masses are different in their size, but our x-axis and y-axis and everything were drawn so that the origin was holding still. Actually, if you like, we put the center of mass right at the origin of our coordinate system. Center of mass was actually, where's the center of mass in this case? Center of mass is very close to the center of the big ball, right? It's inside the ball somewhere. Just a little bit to that side of the center of mass of the ball by itself. This guy's mass, it has some influence. So the center of mass is a little bit displaced to that side, but not by much. So the center of mass is inside the ball, but not right at the center, a little bit to the side of that. So our coordinate system, which is anchored to the table, right? The x-axis was that way, which way I went, but horizontal. It was holding still with respect to the center of mass. Now there's other problems where that's not the case. In fact, in this case, it's not the case, right? When this ball comes flying in, it's moving and nobody else is moving. So this is a case where the center of mass actually is moving with respect to our laboratory coordinate system. So if I wanted to view this in the center of mass, I'd have to actually use relative velocity. So recalculate all the velocities of these balls so that I'm measuring them relative to the center of mass. All right, which is conceptually, I think, a useful thing to do. Many students in this class find it harder to think that way than to stay in the original lab frame and deal with more algebra, but not deal with relative velocity. So there's many ways to solve a problem. You can do it the way. Just for fun, I'll see what happens here for this guy. Kind of like this guy. Anyway, so in this case, right, he bounces off. He's always moving. He doesn't hold still the way he does. This guy comes in and he holds still when he collides. This guy does. Why is that? Well, conservation of momentum, conservation of kinetic energy. In order to conserve kinetic energy momentum, there is no solution where this guy winds up holding still. You have to keep moving a little bit. In fact, if this ball were infinitely massive, like in this case, right, what would happen if I let this guy come in? I shouldn't have done this before. I don't know if he's elastic enough in your collision. But this guy's hardly going to move, right? That just bounces off. He doesn't care. He doesn't care. And that's the only way you can conserve. This is humorous to students, this demo. I don't know. I'll do anything for a laugh. I don't know. It's funny. Anyway, so this is a little tiny ball. It's a big ball. It turns out that if we solve the equations, and what equations am I talking about? These are conservation of momentum and conservation of kinetic energy. Those are all examples of elastic collisions. So both are being conserved. So let's ask a really simple question, and let's do it with the air track. If I have two equal mass objects, one moving initially, one holding still, they collide, and they collide elastically. What possible outcome do we get? Well, let's see. I think it's the same mass. They are, yes. And I'm going to put them like this. All right, I'm going to turn it's going to get really loud, and so you won't be able to hear me. I know you're starting to hear that. But when I do that, I'm going to have this guy zipping in. We use an air track because that makes zero friction, obviously, right? So it's there. So this guy will be floating along over here. I'm going to send him in at some initial velocity, and after they collide, we'll see what happens. It'll be the same as the case over here with the balls, the steel balls, if you only had two balls. So I think you can guess what's going to happen. Let's go ahead and do it. Elastic collision. Right? Bang. Ooh, it was not perfect. That was not perfect. Let me try it again. He should have held still after the collision. I think it's because it's on a ramp, and so this guy started to move. Oh, there we go. He's holding still for me now. That's pretty good. Well, one more time. Oh, they're not the same mass. It's interesting. All right. Well, that last one actually worked fairly well. They weren't perfect. They were sort of moving along a little after the collision. So what we just did, that wasn't a perfect job, but if it really were perfect, these had exactly the same the same mass. Then we have situations like this. We have m1 equals m. You got m2 equals m. So there's only one mass in the problem, right? This guy has some initial. So this is t0, right? This guy's got some initial velocity. We'll call it v1. Geez. All right, fine. I'll say ma and mb. Because I want to distinguish my times from my object. So we'll call this object a and call this object b, and then I can have time 0, 1, 2. Okay, good. So I've got v of object a at time 0. All right. And then this guy, v b0. Well, we're going to say that equals 0. He's not moving in the beginning, right? So he's zipping in, he's holding still, they're on track. A little later, we got time 1. That's when the collision occurs. So he runs into him over here. Collision, right? It's an elastic collision. And then after the fact, what happens? Oh, he's flying out. This guy's, well, we know the answer. The answer is he's holding still. Let's say we didn't know the answer. In fact, that's what we're being asked. We're being asked, what is velocity of object A at time 2, right? Final, right? Okay, so this is v2 of object A, and this guy, he's flying over to the right as well, maybe. So in general, as we saw, excuse me, is it 2 or 1? Oh, no, that's right. v2, a2, v2. Sounds like a robot or something. Okay, great. So after everything's done, as long as we know that it's, so what are we given? We're given that it's an elastic collision. So right away, that tells us, okay, elastic collision, so I know that conservation of kinetic energy holds. We also know that VA1 equals, we'll just call it V, some initial velocity V. We're just given that. And we're told that not V1, V0, it's the initial time. V0, that equals 0, so he's not moving. And we're asked for, the final velocity of object A. What is it? Right? Great. What else are we given? I guess that's all we're given. I think that's all the masses. We're given that MA equals MB, and we'll just call it M. Okay, we're told we have to know what the masses are to solve this, right? All right, so what equations do we have? Oops, sorry. We have conservation of energy. In fact, it's not just conservation of energy. It's conservation of kinetic energy because it's elastic. Right? So I'd say, okay, that means that the final kinetic energy minus the initial equals the work external. Oh yeah, but the external work is 0. There's no forces along the track except between the two. There is a force between. There's springs between them, right? But we don't have to worry about that. That's an internal force. It's not going to affect us, right? It's not going to affect this equation. It's still be true. So that's 0. Oh, great. So what is the kinetic energy now? Final. It's 1/2 m v 1. No, it's not final. Final time is time 2. It's a2 squared. And then we get 1/2 m v squared. And what v is it? It's b2. So our final time is time 2, right? Our initial time is t0. What do we have over here? We have 1/2, and it's all the same m, right? The m's are going to cancel out, really. Everybody's going to same m in front. Also, we're going to the same factor of a half in front. See that? So we've got v squared. Which v do I want? I want object A at time 0. So it's a0. And now I need to add 1/2 mv squared. And which v do I want? I want object B at time 0. Great. Okay, so as I said, halves all cancel out. The masses all cancel out. These are all the same. And we also have a simplification because the problem description says that object 2 was initially at rest. So that means that V0 is 0. Great. So now I can write down the simplified form of this, that object A2 V squared, what is that? It's the sum of the other two. And I'm putting the equation so it's all positive. So this equals, what is it? Did I do that right? I see what I did. This should be B0. No. A0, because A2 is B2 is the one that's 0. That's what I did. No. No, I had it right first time. Sorry about that. I see. Now that's why I have so many subscripts. You might think, well, it confuses me more than all the subscripts, but ultimately I get it right. If I have the lifetime of the universe to solve the problem. Okay, so I have VA0 squared. I think that's valid. This is actually what we were told in the beginning. They gave it a name. They said that this initial guy's got that velocity. That's right. Good. And so that equals the sum of the kinetic energies final. So that's time 2. So I do that. Crisis. Does that look right to you guys? Yeah, I finally got it up there. It took half an hour to get it up there. All right, great. So that's super. But again, this isn't enough to solve the problem, right? Because we have one equation. We know what that is. This is the thing we're looking for, right? It asks for A2, right? But we don't know this yet. In other words, it's the same problem we ran into over there, and we had to use conservation of momentum to get the extra piece of information. Great. What does conservation of momentum tell us? Well, cons of momentum. Okay, what does that tell us? It tells us again, final minus initial equals j. And let's do this in the x direction. So we're calling this way the positive x direction. Now we don't have to worry about which way x was pointing for the kinetic energy because it was all v squared terms. It didn't matter if v was positive or negative, you squared them all. For momentum, you got to keep straight which way your x-axis points because you'll change the signs of everything, right? So let's define the right to be our x direction and say, okay, that means that the first guy, A at time 0, has a positive velocity, right? And then at the end, if we get a negative answer for one velocity, it means it's going the other way. And that can happen. As we saw with the little ball against the big ball, it can bounce off and go the opposite direction it came in. So a negative sign is physically meaningful. You're straight what our signs are. So the final minus initial equals this. This is going to be equal to 0 because there's no external. I'll even put external to remind me. Even though it's sort of implicit. I mean, if this is acting on the system, it has to be some external force acting. And in fact, if you include internal forces, they all cancel out anyway, so it's fine. All right, great. So now let's put our momentum in here. What have we got? Well, we've got, again, it's going to be m times v for every term. The m's are all going to cancel out, right? Because we said it so the m's are the same. This isn't always this easy. Sometimes we'll have different masses, and you'll have to keep track of the factors. But okay, so for final, we got I'll just put m and just leave it alone because we all know the masses are the same. So we have mva2, and we have to add mv. Now I should be careful about what I mean by these here. Maybe I'll put a subscript x to indicate that I mean the x component of the velocity. It can be a positive or a negative number, right? So this is the v2, and again, it's the x component. So I'm putting a plus sign here. I'm going to put a plus sign over here between the two, and I'm going to find out the end based on what signs I get for v2x, vb2x, and va2x. That'll tell me which way they're going. And I have to be very careful when I plug in to a0x that I put the right sign in when I stick in that capital V. It'll be a positive sign in this problem, but it didn't have to be that way. So anyway, there we go. All right, and now I've got a0x, I've got b0x. So which is 0? I think it's b0x with 0. Do you agree? The velocity at time 0, the second guy, yeah, he's 0. Right? So that means that I again have 3 terms. I get one equation with 2 unknowns. It's the same 2 unknowns I have here, so I can solve it. Right? What do I get? The m's all cancel. So I'm just going to write down what remains. I get va0x equals, okay, this thing, let's put in what equals it. No, that's fine. va0x is what? It's capital V. And that equals va2x plus b2x. Just rounding in subscripts. Good. I think that's all correct. And so one thing I can do is just take this equation and plug in here. Right? So if I do that, what do I get? Well, what do we want to find? We were asked to find va2. We were asked to find this. So let's isolate this guy and then stick the resulting equation, which is v minus this, into here. What do I get if I do that? Well, I get v squared equals. All right. This is the thing I want, so I'm going to leave it alone. va2 squared. Let's see. What's the easy way to do this? Oh, I see how to do it. Well, let's just write it out. So here's what we're going to get. We're going to get a bunch of terms that cancel. We're going to get v squared here equals a2 squared, right? That's good. And now plus this. But this thing is what? It's equal to v minus this guy all squared. Minus va2x all squared. Someone see that? And if I write that out, what do I get? Well, I get the initial va2 squared, right? I get plus capital V squared. And I also get plus va2x squared. But I get a minus across term. There's a cross term here. So I get minus 2. You guys remember this? If you have a minus b and squared, you get 2 times, you get minus 2 times a and b. What is that? B and it's, anyway, all right. Good. So I think I did all that correctly. if I take this guy over here, so there's not enough room on the board, I'll get one more line. If I go down here and then cross this guy out with this, those guys cancel, right? And I think if I did this right, I think these guys, I would have expected these guys to cancel. I would have expected these guys to cancel. So I must have made a mistake someplace. I think I made a mistake, because I think the answer is going to turn out to be this times this equals 0. Let's see. Does anyone see if I have a minus sign mistake? I think this looks right to me, that the initial velocity of that one guy equals the sum of the velocities of the two at time 2. That looks right. And this equation says v squared has to equal the sum of them at time 2. That's correct. And now what I want to do is say, all right, oh, I see. So another way I could have done this. Well, I see. So another way I could have done this was say, let's substitute this in for capital V. Now that seems like a stupid thing to do because we already know what capital V is, so why eliminate it, right? But if we do that, then we get an expression where the VA2 squared cancel on both sides of the equation, the VB2 squared cancel on both sides of the equation, and what remains is just the cross term. We get 0 equals VA2, the x component, times V2, the x component. And there's a 2 over here, but that cancels on both sides. It's minus and that cancels because we have 0. So this is an equation I could get by doing a different substitution than I just did. And when you're doing a problem on an exam, sometimes you'll realize halfway through, oh, that's an easy way to do this. I should have done it. Because look at what this tells us. This tells us that one of the two velocities has to be 0 at the end of the collision. In fact, they both could be and still satisfy this equation. It turns out that doesn't satisfy conservation of either energy or momentum. Check it. But this equation, all this tells us is that at least one of the two has to be 0. And in fact, that's the right answer. When this guy bounces off him, what happens? If they're the same mass, and this guy comes in an elastic collision, this is what happens. He winds up not moving. His final velocity is 0, but his wasn't 0. This was the other guy's initial velocity. But think about what happens if this guy missed. So the other possibility is, suppose he had 2 tracks. He comes in and he just misses this guy altogether. Well, he's going to have then the same final velocity as his initial velocity. That's the other solution that we found. This gives us 2 possible solutions, right? Yeah. I got the final expression by substituting in v squared, capital V squared, into this expression. And so instead of having just a sum of 2 squareds, I got the square of a sum. And so there's an extra cross term of V2A and V2B. So what we're going to do next time, I will do a little more of this stuff probably at the end of the lecture, but most of it I'll be talking about midterm review on Thursday's lecture. So we'll see you then.